Good morning, champs. Now let's apply Exergy to a simple air stream. Air enters a device at 600 Kelvin and 3 bar. It leaves at 400 Kelvin and 1 bar. The ambient environment is at 300 Kelvin and 1 bar. Our goal is to calculate the specific Exergy at the inlet, the specific Exergy at the outlet, and the Exergy drop. Specific Exergy tells us how much useful work potential we have per kilogram. So the unit is kilojoules per kilogram. We start with the specific Exergy equation. Specific Exergy equals enthalpy difference minus ambient temperature times entropy difference. For an ideal gas, this becomes an equation with three parts. The first part comes from the temperature difference. The second part is the entropy penalty due to temperature. The third part comes from pressure difference. Now let's calculate the inlet Exergy. At the inlet, the air is much hotter than the environment, and it also has a higher pressure. So we expect a large Exergy value. We insert 600 Kelvin for the air temperature, 3 bar for the air pressure, 300 Kelvin for ambient temperature, and 1 bar for ambient pressure. Using the ideal gas Exergy formula, the inlet specific Exergy is about 187 kilojoules per kilogram. Now we calculate the outlet Exergy. At the outlet, the air is still hotter than the environment, at 400 Kelvin. But the pressure is now equal to ambient pressure. So the pressure contribution disappears. We insert 400 Kelvin and 1 bar into the same formula. The outlet specific Exergy is about 14 kilojoules per kilogram. Now we compare both values. The inlet Exergy is about 187 kilojoules per kilogram. The outlet Exergy is about 14 kilojoules per kilogram. So the Exergy drop is about 173 kilojoules per kilogram. This means the air still has energy at the outlet, but compared to the inlet, it has much less ability to produce useful work. And that is the key idea. Energy can still be present, but its usefulness can be lost. That loss of usefulness is what Exergy helps us quantify.